Thank you very much, Boris. So hopefully you can hear me okay. Please let me know if you can't.
It's perfect.
Thank you. So thank you to Boris and to the organizers for the opportunity to speak to you today. And I'm going to be presenting work from two different studies from our group. And as Boris mentioned, my group is based at Cardiff University, the Schizophrenia Research Group. And both of these studies used exome sequencing data to identify and analyze the role of rare risk alleles in schizophrenia. So I want to begin by giving a very broad overview of our current understanding of the genetic architecture of schizophrenia. So of course we know now that schizophrenia is a highly polygenic disorder with hundreds to thousands of risk alleles distributed widely across the genome and spanning the full allelic frequency spectrum. And studies to date have tended to focus on one of three different classes of mutation. So you have rare copy number variants, we have rare codon variants as commonly identified by exome sequencing, and we also have common alleles. So the latest efforts from the PGC studies have identified 270 common alleles to be associated with schizophrenia with genome-wide levels of significance. So although individually these common alleles only confer small increments in risk for schizophrenia, collectively they're known to account for at least a third of the genetic liability. And it's a common approach in our field to quantify the aggregate risk of all common alleles as a polygenic risk score. So moving down the allele frequency spectrum, studies have now identified at least 12 CNVs to be robust risk factors for schizophrenia. And these CNVs tend to be found in between 1 in 1,000 and 1 in 10,000 people with schizophrenia. And as you can see, there is a nice correlation between the effect size of these CNVs and their frequency. And then finally, for rare codon variants, when considering only published studies to date, there's only been one gene that's been shown to be enriched for rare codon variants in schizophrenia with genome-wide levels of significance, and that is SETD1A, which is enriched for loss of function mutations. But I emphasize here that this is based on published reports, as the eminent schema study, which is going to be spoken about later today by Tajinder Singh, is going to dramatically change this space for rare codon variants in schizophrenia. So I won't speak any more about that. So despite the fact that we know that both common and rare risk alleles both contribute to liability of schizophrenia, there's only been a few studies to date that have investigated the relationship between both common and rare risk mutations within individuals. But to date, the evidence from us and others indicates that in individuals with schizophrenia that do carry one of these rare high-impact mutations, they still have an elevated burden of common risk alleles. However, within schizophrenia patients, the burden of common risk alleles carried by those that carry a rare risk mutation is inversely proportional to the effect size of that rare variant. So for example, individual cases that carry, say, a 22q11.2 deletion or a 3q29 deletion, which have some of the highest odds ratios for schizophrenia, they carry a much lower burden of common risk alleles compared to individuals that carry one of the CNVs with a lower effect size. And these findings support the liability threshold model of schizophrenia, whereby if you have one of these rare variants, you might need fewer common alleles in order to manifest disease. Something else that's become ever more apparent from research over the past 10 years is that pleiotropic effects from schizophrenia risk alleles are widespread. So for example, all CNVs that have currently been implicated as risk factors for schizophrenia are known to also increase risk for additional early onset neurodevelopmental disorders, such as intellectual disability. And also polygenic risk scores for schizophrenia are known to be significantly correlated with polygenic risk scores from other neuropsychiatric disorders, such as autism, developmental delay, and the strongest positive correlations have been found with bipolar disorder. So as I say, we're going to focus on de novo mutations in schizophrenia, and there's several reasons why we want to do that. One of them being that we know that de novo mutations are important risk factors for disorders that are associated with reductions in fecundity, so with a reduced reproductive fitness. And there's evidence for these de novo mutations replenishing risk alleles in conditions like schizophrenia that have been removed by natural selection. So studies have shown that across different neuropsychiatric disorders like schizophrenia, autism spectrum disorder, and developmental delay, there is an excess of loss of function de novo mutations at an exome-wide level compared to a baseline rate. However, this figure from a study published last year by Harrigan et al. Have shown that this excess is greater in the earlier onset neurodevelopmental disorders like autism and developmental delay compared to schizophrenia. But we also know that de novo risk alleles in schizophrenia are not just randomly distributed across genes across the genome. In fact, they're very much concentrated within a relatively small subset of genes known as loss of function intolerant genes. So these are genes for which in large population cohorts, there is a depletion of loss of function mutations compared to a baseline expectation. And there's around 3,500 of these loss of function intolerant genes. There's another reason why we are very much interested in studying de novo variants in schizophrenia, and that's that the de novo study design has been highly effective at identifying individual genes enriched for this class of mutation across different neuropsychiatric disorders. So for example, in autism spectrum disorder, a study published last year, which was based on 6,500 trios, identified 102 genes to be enriched for rare code invariants with robust levels of significance. In developmental disorders, the two key studies that have identified risk genes by looking at de novo mutations are the 2017 Deciphering Developmental Disorder Study, the DDD study, and then more recently, the 2020 DDD study. So in the 2017 study, which is based on 7,500 developmental disorder trios, they identified 94 genes to be significantly enriched for rare coding mutations with genome-wide levels of significance. And then last year in this landmark paper, based on 31,500 trios, which is obviously a huge increase in sample size, they identified 285 genes to be significantly enriched for rare coding mutations. Whereas in schizophrenia, when considering published studies to date, there's only been one gene that's been shown to be significantly enriched for de novo mutations, and that is SETD1A, which I spoke about in my first slide. And this was a paper by Singh et al. In 2016. But there's two primary factors, I believe, why there's only been a few genes or one gene associated with de novo mutations in schizophrenia so far. And that is, of course, sample size. As you can see, when based on published reports, there's far fewer trios examined for de novo mutations in schizophrenia compared to these early onset neurodevelopmental disorders. And also the fact that de novo mutations appear to contribute less to the liability of schizophrenia compared to these early onset neurodevelopmental disorders. So that brings us on to the first study that I want to talk to you about today, where we try to address at least one of those factors. So in this first study, we generated exome sequencing data from a new sample of 613 schizophrenia trios. And we combined this with published data for an analysis of de novo variants in a total of 3,444 trios. And using this data, we had three primary aims. So the first was to try and refine the sets of genes enriched for de novo variants in schizophrenia. The second was, of course, to try and identify novel schizophrenia risk genes. And then finally, we wanted to evaluate the relationship between de novo risk alleles and common risk alleles within samples. So here's a brief overview of our new data set. So we performed exome sequencing of 2,000 individual samples from 674 proband parent trios at Cardiff University. And we did this using Illumina HiSeq 4000 instruments. So all probands had received a DSM-4 or an ICD-10 diagnosis of schizophrenia or schizoaffective disorder. And these trios came from a number of different cohorts. So some of these were recruited by ourselves in Cardiff, such as the Bulgarian and the UK trios, whereas the other cohorts were made available to us through collaboration. So after performing standard exome sequencing quality control, we went from 674 whole trios to 613 trios, upon which we could call de novo mutations and evaluate them for association with schizophrenia. So the first thing that we wanted to look at in our new sample was to assess the quality of our de novo call set, because it's well known that de novo mutations can be enriched for potential false positive events due to quality. So the first thing we did was we compared the rate of de novo mutation in our new sample to the rate that had been reported in previously published schizophrenia trio studies. So in our new sample, we found that the schizophrenia probands on average carried one coding de novo mutation, and around 10% of probands carried a loss of function de novo mutation. So these are variants that have been annotated as nonsense, splice site, or frame shift mutations. And we found that the rate of both all coding or loss of function mutations, or indeed also missense and synonymous mutations in our new sample didn't significantly differ to the mutation rate that had been reported in previously published schizophrenia trios. So this gave us a good indication that we weren't either overcalling de novo mutations due to false positives or undercalling de novo mutations. But we then went on to perform an additional validation experiment where we used Sanger sequencing to confirm the presence of de novo mutations in a subset of our de novo calls. So we randomly took a random sample of de novo point mutations and indels and performed Sanger sequencing on them. And this showed extremely high validation rates, which gave us a good indication that we had a high quality data set. So the first thing we went on to do was to look at whether particular sets of genes were enriched for de novo mutations in our new sample and also in the published trios. And we focused on three different sets of genes. So the first set of genes, which we used as a negative control, are genes that have been shown to tolerate loss of function mutations in large population cohorts. So here the idea is that loss of function mutations in these genes are not subjected to high degrees of selection pressure, and therefore we wouldn't expect these genes to be enriched for de novo mutations within our schizophrenia trios. And indeed, as you can see, this is what we found. So we didn't observe any enrichment of loss of function de novo mutations in these loss of function tolerant genes in our new trios, also published trios, and then a combined analysis of all data, no enrichment. So this provided further confidence that our statistics and our study design was well calibrated. We then went on to look at if we could replicate the known enrichment of rare coding variants and loss of function mutations in these genes that are known to be intolerant to loss of function mutations in general population cohorts. And we indeed replicated this enrichment in our new trio sample, also showed enrichment in the published data. And in our combined analysis of all data, we provided strong evidence that de novo loss of function mutations in schizophrenia are indeed enriched amongst these loss of function intolerant genes. And then the third gene set that we went to look at was these individual genes that have been shown to be robustly associated with rare coding variants in early onset neurodevelopmental disorders, such as autism and developmental delay. So here we used the genes that were implicated in the 2020 Satterstrom autism paper and also the 2017 DDD study, because at the time, the 2020 DDD study wasn't available. So taking the genes implicated in those autism and developmental disorder studies, there was 159 unique genes associated with rare coding variants that we tested for enrichment in schizophrenia. So we found that in our new sample, although there wasn't significant evidence for loss of function de novo mutations being enriched among these genes, the point estimate was greater than 1. And this analysis most likely suffered from low statistical power because it's a small number of trios and it's a relatively small set of genes. But then in our analysis of the published data, and indeed in our analysis of all combined data, we provided strong evidence that in schizophrenia, de novo loss of function mutations are indeed enriched amongst these genes that are known to be risk factors for autism and developmental delay. And given that a lot of these neurodevelopmental genes are themselves classed as being intolerant to loss of function mutations, we wanted to evaluate whether the enrichment that we observed in these neurodevelopmental disorder genes was greater than the known excess that we observed in loss of function intolerant genes. And we indeed found evidence for this. So we found that schizophrenia de novo loss of function mutations had about a 2.44-fold excess in these NDD genes compared to the excess that was observed in loss of function intolerant genes. So this provides further evidence for the pleiotropic effects from rare code invariants in schizophrenia and early onset neurodevelopmental disorders. So we then went on to analyze individual genes to try and identify novel genes as schizophrenia risk factors. And to do this, we focused on loss of function de novo mutations, and we examined all genes in the genome for which we had decent exomic coverage in our sample. So this analysis of 19,000 tests, which would be a Bonferroni correction of 2.6 times 10 to the minus 6. So after Bonferroni correction for multiple testing, unfortunately in our full data set, we didn't identify any new gene to be enriched for loss of function de novo mutations with correction for multiple testing. Our top gene was indeed SETD1A, where we observed 3 de novo mutations, but I should note that all de novo mutations in SETD1A were reported in trios that had been previously published, so we didn't observe any new de novo mutations in our new trio samples. But then the second top gene, which was CUL1, we did observe 3 loss of function de novo mutations, 2 of which were observed in our new sample. But of course, without genome-wide levels of significance, CUL1 certainly needs further support from additional case control studies before we can be confident that it's a novel schizophrenia risk gene. So we then went on to do a more focused analysis of de novo variants in those 159 neurodevelopmental disorder risk genes. Given the prior evidence for the genetic overlap between schizophrenia and neurodevelopmental disorders, we felt that there would be higher prior hypothesis and prior evidence for these risk genes as having a role within schizophrenia. So given that some of these risk genes were associated with loss of function variants in neurodevelopmental disorders, whereas other genes were associated with missense variants in neurodevelopmental disorders, here we tested both loss of function mutations for enrichment in these genes in schizophrenia, as well as missense mutations, and also a combined analysis of both loss of function and missense mutations. So here we had a Bonferroni correction of 477 tests, so 159 genes times 3 different mutation classes. And when we performed this analysis, we did find that one gene, SLC6A1, which is also known as GAT1, was enriched in schizophrenia for damaging missense mutations after this correction for multiple testing. So SLC6A1 is a gamma immunobutyric acid transporter. So one of its functions is to remove GABA, the main inhibitory neurotransmitter, from the synaptic cleft. And there has indeed been prior evidence for disruption of the GABAergic neuronal signaling system in schizophrenia. And this has come from research based on copy number variants. So given the nature of that analysis, of course, we know that SLC6A1 is associated with a number of other neurodevelopmental disorders. And in our analysis, the evidence for it being enriched in neurodevelopmental disorders came from the work of Satterstrom et al., which was published last year. So I'm showing a figure taken from this Satterstrom paper, which shows the genes that have been implicated in autism through rare code invariants, and the number of times in autism that those genes are disrupted or affected by missense mutations on the y-axis, or disrupted by loss of function mutations on the x-axis. And what they found is that although the majority of genes were disrupted by loss of function mutations in autism, there was 4 genes that were preferentially disrupted by missense mutations. And as you can see, the top gene to be disrupted by missense mutations in autism was our new candidate, SLC6A1. So we wanted to perform a meta-analysis of the autism de novo data and our schizophrenia de novo data to see if this strengthened the evidence for its association with both these disorders compared to the evidence that just came from the autism study on its own. So in our analysis of the autism dataset, we found that SLC6A1 was enriched for missense variants with a p-value of 8 times 10 to the minus 11. But then when we included our new schizophrenia data into this analysis, we found that the strength of association for missense mutations increased by several orders of magnitude. So this provides further support that missense variants in this gene indeed do contribute to schizophrenia. So here I'm showing another figure taken from that Statistron paper, which shows the location and the type of mutation observed in SLC6A1 across different neuropsychiatric disorders, because it's known that this gene is also associated with earlier onset developmental disorders and also epilepsy. So of course we observe missense mutations in schizophrenia, and as I've just discussed, we observe missense mutations in autism. The proportion to missense to loss of function mutations is slightly different for developmental delay and for epilepsy. So for example, in epilepsy, around 50% of the mutations observed in this gene are loss of function, whereas in earlier onset neurodevelopmental disorders, around 30% of the mutations in this gene are loss of function. So this suggests that the type of mutation in SLC6A1 may be a factor in determining risk for particular disorders. When looking at the location of mutations in this gene, there's also some evidence for a clustering of mutations within particular protein domains across disorders. So for example, there's some evidence for a clustering of mutations in autism in the transmembrane 6 protein, whereas there's some evidence for clustering of mutations in the transmembrane 7 protein in epilepsy. But in schizophrenia, given that we only observe 3 mutations in this gene, we're underpowered to assess for any clustering of mutations, but we note that all 3 mutations in schizophrenia affect different protein domains. So given that SLC6A1 is a known risk gene for a number of different neurodevelopmental and neuropsychiatric disorders, and the fact that comorbid neurodevelopmental phenotypes are observed in schizophrenia at a rate higher than that at which they're observed in the general population, it's important for us to evaluate and assess whether the schizophrenia patients that carried mutations in this gene had any additional comorbid developmental phenotypes. So for our 3 schizophrenia carriers, we were able to obtain additional phenotypes for 3 of the patients, and we observed no evidence for any comorbid developmental phenotypes in these schizophrenia SLC6A1 carriers. So for example, in one of the patients, there was no signs of epilepsy or autism. Their premorbid personality was well adjusted. And in the other patient, they completed secondary school and their case reports had no evidence of developmental delay or epilepsy. So moving on to our final aim for this first study, where we wanted to evaluate the relationship between de novo and common risk alleles within samples. So in order for us to evaluate common risk alleles in our trio cohort, we used a method that was published a number of years ago by Viner et al., known as the polygenic transmission disequilibrium test. So in this method, we're testing whether common risk alleles for schizophrenia are over-transmitted from the parent to the child in what's known as a p-TDT deviation test. So in this test, we take the polygenic risk score from the child and we subtract from it the mid-polygenic risk score for both parents, so the mean polygenic risk score amongst the parents. And in a control PRS setting, so for example, individuals without schizophrenia, or when we're looking at a control PRS, polygenic risk score that's not believed to be correlated with schizophrenia, this is the distribution of polygenic risk scores that we would expect to see amongst the probands, the offspring, and also for the mid-parental polygenic risk score. So we wouldn't expect to see any difference in the mean PRS amongst these distributions. However, in a case polygenic risk scenario where we would hypothesize that there would be an overtransmission of polygenic risk, you would expect to see the mean polygenic risk score amongst the proband to be greater than the mean polygenic risk score amongst the mid-parental scores. And indeed, this is what has been previously reported in studies of autism, where they found that the autism polygenic risk score was overtransmitted to the autism probands. But in the context of our work, what was interesting in that study is that they didn't find any difference in the degree of overtransmission to the probands with autism that carried an autism associated de novo mutation compared to the probands that didn't carry an autism disease-associated de novo variant. So here I'm showing results of the polygenic disequilibrium test in our schizophrenia probands, looking at different polygenic risk scores. So unsurprisingly, we saw a significant overtransmission to our probands of schizophrenia polygenic risk, which is highly significant. We also observed a overtransmission of polygenic risk scores for bipolar disorder, which provides further support for the genetic overlap at the common allele level between schizophrenia and bipolar disorder. And we didn't observe any significant overtransmission of polygenic risk scores for type 2 diabetes, which we tested as a negative control. But then in the context of our work, we wanted to see whether the degree of schizophrenia polygenic overtransmission differed between probands that carried a pathogenic de novo mutation and those that didn't. So in this figure, I'm showing on the y-axis the degree of polygenic overtransmission. And then in red and in blue, I'm showing this polygenic overtransmission in schizophrenia probands that either carried a particular mutation, rare mutation in blue, and probands that didn't carry that mutation in red. So for example, when we stratified our proband sample into those that carried a synonymous de novo mutation in a loss of function intolerant gene or a neurodevelopmental disorder risk gene to probands that didn't carry one of these mutations, we didn't find any difference in the degree of polygenic overtransmission amongst these samples. However, when we stratified our probands into those that carried either a loss of function de novo mutation or a CNV deletion de novo mutation affecting one of these genes, we found that the degree of polygenic overtransmission to these probands was significantly less than the degree of polygenic overtransmission in probands that didn't carry one of these mutations. And we found similar effects when we looked at just loss of function de novo mutations or CNV deletion de novos on their own. So again, this work here provides further support for the liability threshold model of schizophrenia, but it also provides a further line of robust evidence that mutations in these genes are indeed risk factors for schizophrenia. To summarize this first study, in our new trio sample, we confirmed the enrichment of loss of function de novo variants in schizophrenia within loss of function intolerant genes. And we also showed that de novo variants in schizophrenia are highly enriched among genes that have been previously shown to be risk factors for neurodevelopmental disorders. We implicate SRC601 as a novel schizophrenia risk gene. However, we note that this is without genome-wide levels of significance, and therefore additional support in other trio samples or large case control samples is required before we can consider this a definitive schizophrenia risk gene. We show that schizophrenia and bipolar polygenic risk scores are overtransmitted to our schizophrenia probands. And then we also show that carriers of candidate schizophrenia-related de novo variants show less overtransmission of schizophrenia polygenic risk compared with non-carriers. So I now want to move on to presenting research from a second study, which is unpublished. And in the second study, we wanted to do a thorough investigation of the nature of pleiotropic effects from rare codinvariants between schizophrenia and early onset neurodevelopmental disorders. And specifically here, we wanted to evaluate whether pleiotropic genes are enriched for the same class of mutation. So for example, loss of function or missense variants across these disorders, or are pleiotropic genes enriched for different classes of mutation across these disorders? So I want to begin by discussing the types of pleiotropy from rare codon variants that we investigated. So the first type is genic pleiotropy, and this is defined as when the same gene is enriched for rare codon variants in different phenotypes. And we investigated this under two different scenarios. So in the first scenario would be where the same gene is enriched for different types of mutation in different disorders. So for example, we might see loss of function mutations in this gene enriched in early onset neurodevelopmental disorders like autism or developmental delay, whereas we might see missense mutations in this gene enriched in schizophrenia. And then in the second scenario is whereby we would see the same class of mutation within the gene to be enriched across these disorders. So this first scenario would imply that although the same gene is associated with these disorders, it's possible that there's different changes in gene function represented by the different classes of mutation are more important for conferring risk for these disorders. Whereas in the second scenario, this would imply that it's similar changes in gene function that confer risk for these disorders. However, it's well known that within genes, different variants of the same class can sometimes have different pathogenic effects or different functional consequences. So therefore, it was also important for us to evaluate evidence for allelic pleiotropy. So this is defined as when the same variant is associated with different phenotypes. And allelic pleiotropy would indeed imply that similar changes in gene function confers risk for different disorders. So as mentioned in the previous work that I presented on, and also has been shown by other groups, there's now strong evidence for this first type of pleiotropy, so for genic pleiotropy across schizophrenia and neurodevelopmental disorders. And some of the strongest evidence for this to date from rare codon variants has come from that work I presented, where we show that neurodevelopmental risk genes, neurodevelopmental disorder risk genes, are enriched for rare codon variants in schizophrenia. However, this study by us and similar work by others didn't evaluate whether it's the same type of mutation in these neurodevelopmental disorder phenotypes that are enriched in schizophrenia. And therefore, the degree to which pleiotropic effects are confined to the same functional class of variant within genes is unknown. The degree to which the exact same alleles within genes across different disorders is less clear. So the evidence for allelic pleiotropy is much less clear compared to the evidence for genic pleiotropy. However, there have been observations of plausible pleiotropic variants across schizophrenia and neurodevelopmental disorders. So for example, in this gene SETD1A, which as mentioned is associated with loss of function variants in both schizophrenia and neurodevelopmental disorders, there is a single allele, so an indel, which has been observed multiple times in people with schizophrenia and in developmental disorders. So this indeed implies that this is a pleiotropic variant. However, there haven't been any genome-wide studies yet testing whether specific variants observed in people with neurodevelopmental disorders are as a group significantly enriched in schizophrenia. So that brings us on to the two primary aims of this second study. So the first is where we wanted to do a thorough investigation of genic pleiotropy. So here we wanted to evaluate whether genes associated with specific classes of de novo mutation in neurodevelopmental disorders are enriched for the same class of de novo mutation in schizophrenia. And then in the second aim, we wanted to investigate allelic pleiotropy. So here we want to evaluate whether specific variants that were observed as de novo mutations in people with neurodevelopmental disorders are enriched in schizophrenia. So for this first aim, we began by trying to identify specific genes enriched for particular classes of mutation in neurodevelopmental disorders. And here we use data from that 2020 Deciphering Developmental Disorder study by Kaplanis et al., which is based on 31,000 new developmental disorder trios. So using the results from that work and specifying an individual gene's exome-wide level of significance as being 2.5 times 10 to the minus 6, we identified 127 genes that were specifically associated with loss of function mutations in developmental disorders, 103 genes that were specifically associated with missense mutations in developmental disorders, and 53 genes that were independently associated with both classes of mutation in those developmental disorders patients. So these were the 3 gene sets that we tested for enrichment of rare codon variants in schizophrenia. So to do this, we used the schizophrenia trio sample that I previously spoke about, so 3,444 schizophrenia trios. And we compared the observed rate of de novo mutations amongst these gene sets to that expected, and the expectation being based upon the known per gene mutation rates that have been well studied and shown as an effective way of evaluating whether there is an excess of de novo mutations amongst particular genes. So here are the results from that analysis. So for those genes that were found to be specifically enriched for loss of function mutations in developmental disorders, we found that as a group, they were significantly enriched for loss of function mutations in schizophrenia. However, we didn't find any evidence that these genes were, as a group, enriched for damaging classes of missense mutation in schizophrenia. When looking at those neurodevelopmental disorder genes that were specifically associated with missense mutations, we found no evidence that as a group those genes were enriched for loss of function mutations in schizophrenia, but we did find evidence that as a group they were enriched for missense mutations in schizophrenia. And then for those genes that were both associated with loss of function and missense mutations in developmental disorders, we again found that these genes were enriched for both classes of mutation in schizophrenia. So collectively, these findings provide evidence that pleiotropic genes are enriched for congruent, so the same types of mutation in both schizophrenia and early onset neurodevelopmental disorders. So moving on to our second aim, where we wanted to investigate allelic pleiotropy. So here we first needed to identify specific alleles, so specific mutations that are likely to be causal for early onset neurodevelopmental disorders. So here again, we turn to the large published trio studies for neurodevelopmental disorders, so the Kaplanis study, and also the paper by Satterstrom et al. For autism. And taking the de novo variants that were published in those studies, we found that the de novo mutations in these disorders mapped to 46,772 unique single nucleotide variants. So these were the exact mutations that we wanted to test for enrichment in schizophrenia. But we first stratified these mutations into 2 variant sets. So the first was our primary variant set that we hypothesized would be enriched in schizophrenia. And that's because this set contained mutations with characteristics known to be pathogenic for these developmental disorders. So this included those de novo variants that were annotated as either loss of function variants in loss of function intolerant genes, or missense variants that were predicted to be pathogenic according to the MPC score. And then in our negative control test, we examined all remaining variants. So these were the loss of function de novo mutations not in loss of function intolerant genes, as well as missense mutations with lower MPC scores, as well as all synonymous de novo mutations. So to test these variant sets for enrichment in schizophrenia, we again used the same schizophrenia data set, and we compared the observed rate of de novo mutations in these variant sets to that expected in our sample, with the expectation being based on trinucleotide mutation rates. So here are the results from that analysis. So for our negative control test, we didn't observe any enrichment of these NDD variants in our schizophrenia sample. So 8 were observed, whereas only 9 were expected. However, for our primary NDD variant set, we found strong evidence that these mutations observed as de novo events in people with NDDs were indeed enriched as de novo mutations in our schizophrenia sample. So we observed 9 NDD variants in our sample, whereas only 1 was expected based on mutation models. And it's important to note that this excess here adjusts for the known background excess of constrained de novo variants in schizophrenia. So it's not simply reflecting that known excess of constrained PTVs or constrained missense mutations in schizophrenia. So we broke down these primary NDD variants into those that were just loss of function mutations or those that were just missense mutations. And we found evidence that both classes of mutation were indeed enriched in schizophrenia. So here are the 9 variants that we observed as de novo mutations in both schizophrenia and that were observed as de novo mutations in early onset neurodevelopmental disorders. So we note that 5 of these mutations affect genes that are known neurodevelopmental disorder risk genes, which provides further support for their pathogenic effects. And we also note that 4 of the mutations where the exact mutation was categorized as being pathogenic in either the Decipher or the ClinVar database. And 3 of them are known to cause neurodevelopmental disorder syndromes. So interestingly, from one of the talks this morning, one of the mutations that we observed in schizophrenia, which affected KMT2D, is a known risk mutation for Kabuki syndrome. Another mutation is a known causal mutation for neurofibromatosis. And then finally, another mutation is known to be causal for Oka-Chung neurodevelopmental disorder syndrome. So given the known overlap between schizophrenia and other neurodevelopmental disorders, and the fact that several of these mutations are known to be pathogenic for particular disorders, it was of course important for us to evaluate any additional neurodevelopmental phenotypes amongst these schizophrenia patients. So we were able to access additional phenotype data for all 9 patients. And we note that 4 of the probands had an early age of onset before the age of 18, but only 2 of the probands had evidence for low premorbid cognitive function. So one of them was indeed the proband with the KMT2D mutation. So this individual with schizophrenia had normal delivery and achieved normal milestones, but they left secondary school without qualification and has since had supported employment. And then the other proband with low premorbid cognition was the individual with the ORTS2 mutation, and they had delayed developmental milestones and had supported schooling for secondary education and had received support for learning disability. However, we didn't find any evidence from either the published case notes or within our samples that these individuals had a recorded diagnosis of these neurodevelopmental disorder syndromes. So to summarize this second study, we showed that genes associated with specific classes of de novo variant in NDDs are most commonly enriched for the same class of de novo variant in schizophrenia. We show that specific de novo variants that are observed in people with these early onset neurodevelopmental disorders are indeed enriched in people with schizophrenia. So this provides evidence for pleiotropy at the allelic level across these disorders, and indeed implies that in some scenarios, in some situations, it's the same changes in gene function that confers risk for both schizophrenia and the early onset neurodevelopmental disorders. And collectively, these findings support the hypothesis that at least some forms of schizophrenia lie within a continuum of neurodevelopmental disorders. So I'd like to acknowledge lots of people that made this work possible. So the people from the Schizophrenia Cardiff group. So this work was primarily led by Mick O'Donovan, Mike Owen, and James Walters. Also like to acknowledge collaborators and our funders. And just like to note that the first study, if you're interested in looking at it further, was published last year in Nature Neuroscience. And that second study, which is unpublished, is available on bioRxiv. So thank you very much. Happy to take any questions or comments.